Welcome to another podcast. This episode we're going to be taking a look at a process called induction, via what's usually called the induction machine. Let me describe this simply as what we want to show and kind of how we're going to show it. What we would like to show is that a statement that depends on n is true for all values of n in the natural numbers. And so one of the first things that you're going to find is that the induction machine requires or depends on the natural number system. You can think of this as being sort of the iterates. So it depends on having an iteration, which is why oftentimes this is tied to algorithm checking or something called a loop invariant. So the induction machine is really a way of testing to see whether a loop or an algorithm works and does what it says it's supposed to do. But in general, it's a way to mathematically prove statements that depend on the natural numbers. So suppose we have a proposition. We want to show that the proposition is true for every value of n that we could possibly put into it. For example, suppose we wanted to show that the sum of the first n integers is equal to n times n plus 1 divided by 2. So the sum of the first n integers is equal to that. This is our statement p of n, and we need to come up with an algorithmic way of showing that to be a true statement. So here's how we go about doing this. Step one in this process is you show that the initialization is true or holds. So show that the value for n equal to 0 holds. And in general, this is called the base case. And you don't have to start with n equal to 0. But you can't backtrack. So for example, if I start my base case at n equal to 5, then the result is proved true for n greater than or equal to 5. But since I said I wanted to show it true for all n in the natural numbers, then I'm going to show the base case as the first natural number, which is 0. So I want to show that the case p of 0 holds. Because of this step, oftentimes we think of this as being logically equivalent to the well-ordering principle or involving or invoking the well-ordering principle, and that is indeed the case. Smallest counterexample fits in here as well. All of these things are logically equivalent methods, but induction is far and away the most common of those methods. So the second step in this process is that you assume the statement p of n holds for some n in the natural numbers. In other words, you run it through the loop, you run it through the process, and let's say you check the first 10 cases. So you check the first 10 cases, they all work out, and you assume that that process works arbitrarily so that any number of cases you specify can check it and the result holds. We assume that. That's called the induction hypothesis. And then the final step in this result is, okay, if it works for some arbitrary number of n, show that I can run it through one more time and get the n plus first step. So in other words, I want to show that p n plus 1 holds. Now, as a logic argument here, the argument that we're making is the following. P of 0, and if I know for all k, P of k implies that P of k plus 1 is true, then those two things together imply that for all n, P of n holds. So this is the logical form of mathematical induction. Now, since we're going to be using this particular proof method all throughout the rest of the course, it's probably worth our time to go ahead and show that this is indeed the case, to show that this argument is indeed valid. And this is going to be a proof by contradiction. So for the purposes of contradiction, I want to assume that for some value of n, P of n is false. Now, this starts off exactly as you would expect it to. If you remember our discussion in class of how proof by contradiction works, you negate the right-hand side of the implication, so that's there exists an n such that P of n is not true. So we start with that, and we're going to work backwards from that. So if there exists an n, so which P of n is false, let's go ahead and point that object out. So let's let the value n0 be the least n so that P of n0 is false. In other words, it's the smallest counterexample. So this goes back to what I was saying before. The well-ordering principle guarantees we have a least element in the natural numbers, and in this case guarantees we have a smallest counterexample. So these are used in the proof of showing that proof by induction is valid, which is why oftentimes people say that they are logically equivalent methods of proof, and they are. It's just induction is a little bit easier to use normally. So let's identify the smallest counterexample here, P, such that the proposition P is false for that value. Now, n sub 0 cannot be 0 since P of 0 is true. So we know that P of 0 is true, and we have the induction hypothesis. So working backwards, if we assume this is false, we have to abide by these particular cases. So n0 cannot be 0 since P of 0 is assumed to be true. Thus, n0 is 1 plus some value n1. You could think of it this way, that the smallest value that n0 could be is 1. So this is where 0 is less than n1 is less than n0. Since n1 is less than n0, then Pn1 is true, since, and this is because since n0 is the smallest counterexample. So since n1 is smaller, P of n1 must be true because the first time it's false is at n0, which is larger. So P of n1 is true since n0 is the smallest counterexample. However, this implies that P of n1 plus 1 is true by the inductive hypothesis. Because we have this condition as well, which says that if you have one step, the next step in the chain is also true. So if I know P of n1 is true, then P of n1 plus 1 has to be true. But we know here that P of n1 plus 1 is equal to P of n0, which is false. So you can see here that we've reached the contradiction we've required because I have both P of n0 being false and P of n plus 1 being true. So this right here is equal to P of n naught. So I have P of n naught is false here, but I have it's true here. So I've reached a contradiction to that. So it follows that there doesn't exist an n such that P of n is false. So it follows that for all n, P of n is true. So think of it this way. I started off by assuming these, and I supposed that the conclusion was false. So for the purposes of contradiction, I supposed the conclusion was false. I then worked and showed that if we proceed from the assumption that the conclusion's false, that ends up leading us to a contradiction. Therefore, the conclusion must have been true all along. That is this logical statement. If you have a base case, notice how I used both of them. I used the base case here, and I used the induction hypothesis here. So it requires both. But if you have both the base case and the induction hypothesis, then you can conclude that your statement P of n is true for every value of n. All right, we're going to be doing more induction proofs in the next two videos, so you'll get a better handle on how to structure this argument. But I thought it was important for me to prove to you in this video that it works. It works very well. It's dependent upon the ideas of the well-ordering principle and smallest counterexample, and it's also a great example of proof by contradiction in play. It's also related to algorithm checking and loop invariance as well. So there's a lot of things in both mathematics and computer science that hinge on being able to do induction arguments, and you're going to see that sort of unfold here over the next week in class. All right, thank you for watching.